Now let us have one example of a random pair to be represented either in Cartesian domain or polar domain. So we want to know what's going to be the distribution representation in polar or Cartesian. So far, what we have seen was that the polar representation and Cartesian representation they are related. So the pair xy, so if you have r and theta, you can calculate x and y using these two equations. And similarly, if you have x and y, you can calculate r and theta. So there is a one-to-one relationship between these two representations. So it's like a transformation. So if you have, let's say in the first one, you have r and you have theta, so you have two random variables, and then you have two output random variables x and y. Or the second transformation here is that you have x and y, you can uniquely calculate r and theta. So if you have the joint distribution of f of r and theta, we shall be able to calculate or express distribution of x and y in terms of that, and vice versa. So we want to know what is the relationship between these two representation, these two distributions. So in this example, consider a point here which is this point is this is x, this is y, this is theta, and this distance is r. So what we can do, we can consider a small angle delta theta, and we can consider a small increase in radius of delta r. So from here to here is delta r. So if I extend here delta r and extend here another theta angle here, and if this delta r and this delta theta, so from here this distance is, this angle is delta theta is the angle, the difference between these two angles, and because this is r, so the length of here is going to be delta theta times r. So you know that this length, this arc, is equal to that. So this is equal to length of the arc. So if delta theta is a very small number and delta r is a very small number, so this is like a rectangle. So this area, because it's a rectangle, is going to be, and this is perpendicular, is going to be delta r, delta theta times r. So the red area. So if you calculate the area of this, so the probability of your point, probability that the pair of x and y falls in red area is equal to the, because we know by definition of the PDF, if this red area is teeny tiny, is going to be the area, which is going to be this number, delta r, delta theta r, and then fx y of x and y. However, if you look at this probability of, let's say, your point being in this area, means that r is bigger than your small r and smaller than r plus delta r, and theta is bigger than your small theta and theta plus delta theta. Obviously, by definition, is this equal to PDF of f of r and theta of r and theta, delta r, delta theta. So these two probabilities are equal, and then you could simplify it. So this term and this term, they will be simplified. So from here you can obviously see that there is a relationship between the distribution in Cartesian and polar. So in summary, probability that you have x and y in the red area is equal to that, and probability that you have that. So these two guys are equal. So if you equate that, so these two will disappear, and then from here what I conclude is that fx y of x and y is equal to r f r theta of r and theta. Obviously you should remember that x is equal to r cosine of theta, y is equal to r sine of theta, and r is equal to square root of x2 plus y2, and theta is equal to arc tan of x and y. So you could substitute these two guys here, or you could replace these two guys this side and obtain two different equations which gives you the distribution of distribution Cartesian domain in terms of distribution polar domain, and vice versa. So remember that the colored area is approximately a rectangle which has this area, and the area in the Cartesian domain and in the polar domain, the ratio of the two areas is equal to this divided by this, which is in, and this guy is called Jacobian, that we could see. And obviously here fx y of x and y is equal to f r and theta of x and r and theta, and then you have a factor of r here which is Jacobian. Obviously the Jacobian in one domain to the other one is equal to the inverse of the other one. So this is the first equation, which gives you, if you know the distribution in xy domain, so you can use this guy. So this r is the ratio of the areas, which is Jacobian. Or if you know the distribution of f of r and theta, and you want to calculate the distribution of fx and y of x and y, so you have to get 1 divided by r, which is x2 plus y2, and then here you have to write a square root of x2 plus y2 and arc tan of x and y. So you have both relationships. So if you transform from Cartesian to polar, you use this equation, but if you transform from polar to Cartesian, you use this equation.